So odds are you're on the internet these days. But what does that actually mean? And indeed, this internet that we use very often these days for messaging, for email, for browsing the web, and other services still, there's a whole infrastructure that underlies it that is increasingly powering new ideas, new startups, new companies, new businesses, as well as new forms of communication among humans. And yet, like most every topic we've explored, you'll realize that while it's very complex perhaps up here, or certainly seems complex up here, if we begin with some of the fundamentals and then layer and layer and layer on top of those, do we pretty quickly get back to today's technology, but with a much better understanding of what's going on from the ground up. So here is a bit of alphabet soup. Odds are you might have seen one or more of these acronyms to date: IP, DHCP, DNS, TCP, UDP, ICMP, and so many more. These are all examples of something called protocols, where protocols are kind of like languages that computers speak with one another. They're not programming languages, so they're not used by humans to make computers do things or follow instructions per se. A protocol is really a set of conventions that two computers or two computer programs might use when intercommunicating. And so what's an example of a protocol in the real world? Well, we humans have some silly protocols, one of which here is culturally when you meet someone to extend your hand, and then he or she presumably extends their hand, and you do this for who knows what reason. And now you've sort of completed that social transaction. But it's a protocol in the sense that when I extend my hand, most any polite other person knows that they're probably supposed to extend their hand as well, embrace for a moment, and then complete. And the protocol says, too, you probably shouldn't do this for terribly long. And so there's these rules of thumb, or actual rules that you follow when implementing protocols. And so computers, great as they are at following rules, very often use protocols when they intercommunicate in order to get data from one place to another. So let's tell exactly that story. If you're on the internet, indeed right now on the internet, what does that actually mean? And how can it help us solve problems ultimately, having access to this inter-networked infrastructure? Well, let's consider what happens when I first visit my favorite web page, for instance. If I go ahead and visit something like facebook.com, I go ahead and log in, and I'm immediately presented with my news feed. Or maybe your favorite website is Gmail, or your favorite website is Bing, or maybe your favorite website is any number of other places you might go on the web, all of which take in as input a request from you and produce ultimately output, the screen that you ultimately see. But how does that data get from one location to another? Let's begin to draw a picture, perhaps. And this picture might be representative of your own home network, or maybe your campus network, or maybe your office network. But generally speaking, you are on the internet, maybe with your phone or your laptop or your desktop device. And we'll just depict that as this sort of abstract laptop here. So that laptop somehow wants to communicate with a web server elsewhere, Facebook, Google, Bing, whatever. And we're just going to present that as way over here in the picture in a really big corporate office building, perhaps. And inside of that building are the servers that compose that particular website. But how do I get data from that server, which if it's Google or somewhere else might be all the way in California or halfway across the world, and back to my laptop? Well, somehow I have to be able to send messages to it and receive messages from it. And of course, in between me and this resulting website is what we'll generally call the internet. It's kind of conveniently drawn as a cloud here, which is another semi-technical term that's come into vogue in recent years. And the cloud really just refers to internet services these days. It's not a technical term unto itself. It's just a sexier term than saying, my business is on the internet. Oversimplification, and we'll come back to that before long, but you can assume near that the internet is somehow this delivery mechanism. It somehow gets data from point A to point B and back. But how does that work? If my data is coming in as input and it's reaching eventually its destination, and then a response is coming back in this direction, what's actually going on underneath the hood there? Especially since, in the story at hand, all I've typed is something like facebook.com or gmail.com or the like. Well, it turns out that your computer these days, when you first turn it on and you connect to like the Wi-Fi or in a room, or you connect with an Ethernet cable to the wired network, your computer receives some information automatically. Your computer speaks a protocol called DHCP typically, Dynamic Host Configuration Protocol. But in most of these cases, the acronym isn't really what's important, certainly. It's what the protocol itself does. And in this case, this Dynamic Host Configuration Protocol dynamically configures hosts via a protocol, if you will. So what does this mean? Essentially, DHCP says this. When you turn on your computer or you take out your phone for the first time and you're connected on Wi-Fi or to a wired network, it says, hello, world. I am alive. I would like to be given an address so that I can communicate with other computers on the internet. It's not quite that verbose, perhaps, but it is a question. Hey, computers around me, please give me an address. And what it gives you is what's called an IP address, Internet Protocol. So just as in the real world, where physical buildings have historically been uniquely addressed with postal addresses, like Harvard's computer science building is at 33 Oxford Street, Cambridge, Massachusetts, USA. 02138 is the more precise zip code as well. That uniquely identifies that building in the world. So does my computer need an address. And it's not going to be some free-form address like that in words. It's actually going to be a numeric address. Specifically, I'm going to get an IP address of the form number.number.number.number. So 4 numbers separated by dots. Each of those 4 numbers happens to be a byte long, or 8 bits. So each of these numbers, therefore, is between 0 and 255. And so this means, long story short, that the total address is 32 bits, 8 plus 8 plus 8 plus 8. And that means there's 4 billion possible addresses in the world. And that's great, because people got a lot of computers and a lot of laptops and a lot of desktops and servers these days. But it turns out we're actually running out because we have so many such devices. So there's a newer version of IP that's increasingly being used called IP version 6. We're talking here about IP version 4 since it's so omnipresent. And IP version 6, just so you know, uses 128 bits for its addresses, way more than 32. So we'll be good to go for some time. But DHCP gives me this address, an IP address of the form something.something.something.something. And the purpose of this address is to help my data get from point A to point B. And indeed, anytime my computer sends a request out on the internet, like Facebook, please show me my newsfeed, or Gmail, please show me my inbox, my computer has to use that IP address. So much like if sending a letter in the real world, you might have an otherwise blank envelope, and you might want to send a message to someone else in the world. You might write their physical address, but in the computer world, we might write something like 1.2.3.4 in the to field, assuming that this is the IP address to which we want to send this data. Meanwhile, my from address might be 5.6.7.8, so I'll write it in the top left-hand corner by convention, whereby that indicates to the whole internet, this is where this request came from. Now, I know my origin address, the source address here at top left, because DHCP told me. How do I know 1, 2, 3, 4? How do I know the IP address of Facebook.com or Gmail.com? Right? We don't live in the world of 800 numbers anymore, where you dial 1-800 something 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 something, and you have to advertise your phone number per se. We don't necessarily live only in the world of 1-800 collect anymore, where we had these mnemonics where you had letters mapping to numbers just to help remember it. We went full in on this idea of mnemonics, such that now we have Facebook.com and Gmail.com, and no numbers whatsoever for us humans to remember. So thankfully, turns out there's another system in this world, another acronym, if you will, a new one now, called DNS, Domain Name System. So there are also in the world not just DHCP servers that hand people IP addresses from their local network. There's also DNS servers whose purpose in life is to convert domain names to IP addresses and vice versa, and a few other features as well. Now, what does that mean? That means that when my Mac or my PC sees little old me, the human, typing Facebook.com or Gmail.com, my laptop contacts a nearby DNS server and says, hey, my human has asked me for Facebook.com. What is its IP address? And a DNS server's purpose in life is to answer that question and say, oh, Facebook.com, it's 1.2.3.4. Use that address instead. Now, thankfully, my computer can now write that number on its virtual envelope, so to speak, and then pass that envelope out to the internet. And because of these numeric addresses, it will be properly, hopefully, routed across the internet to its destination. Because it turns out inside of the internet here, interconnecting everything in between point A and B are things called routers, or gateways. And I could draw this picture in any number of ways, but the point is that it's just so darn interconnected. And indeed, there might be even more pathways still, or maybe even fewer pathways. Indeed, on the internet, there's often multiple ways for data to get from one point to another, some shorter, some longer. But there's this resilience, this redundancy. And this was a feature back in the day, especially insofar as the internet had militaristic origins. It was meant to be redundant so as to withstand failures of one or more of these nodes, these dots in the picture. Now, each of these dots is just a server, really, a special server called a router or gateway, whose purpose in life is to do exactly that, to route data. Upon receiving a virtual envelope like that one, it looks at the to address, realizes, ooh, this is destined for 1.2.3.4. I know that that address is over this way. Meanwhile, if it gets another envelope from someone else, it might say, ooh, this is some other address. It's going to go this way. And so routers have multiple cables, or they have multiple virtual network connections elsewhere, or wireless connections. Any number of possible connections might they have to other routers. And so it can route it to its next hop, so to speak. And generally on the internet, within 30 hops, within 30 transmissions from router, 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 will your data get from one point to another. And it might not follow the same path each time, but it will traverse this so-called internet. And so that's kind of what the internet is. It's this collection of routers, and it's this collection of networks, a network of networks that is incredibly interconnected in different ways. So DHCP gives me an IP address, so I have a unique IP address. DHCP, turns out, also tells me what the IP address is of my local DNS server, so I know whom to ask to convert domain names to IP addresses. But once I have that, I can now use a protocol called TCP to send my data reliably, typically from one point to another. So whereas IP is responsible for a few things, one of its most important functions is this notion of addressing and standardizing how things are addressed. But TCP, one of its most salient features is to guarantee, with high probability, delivery. And what I mean by that is that bad stuff can happen in the middle of the internet. These routers can get really busy. They can get really congested and overloaded. And so routers might virtually drop packets. They might receive so many packets at once, they just can't, like a human, deal with it all at one time because they have a finite amount of memory or RAM or disk space. And so they drop them, so to speak. They just delete them, and they expect the senders to resend them. TCP is a protocol, another agreement between computers, that if the receiving computer realizes, I got some of your packets, but not all of them, TCP mandates, much like our human handshake, that something next should happen. TCP says my laptop should retransmit that virtual envelope. But TCP allows us to do something more than guarantee, with high probability, delivery of data. It also allows us to multiplex among services. Or put more simply, it allows a server to receive different types of data for different types of services. For instance, web services on the server, email services, chat services, and the like. And so it turns out that on this virtual envelope that gets sent from a computer to a server, it's actually not sufficient for there to be the return address and the IP address of the destination. I also need to specify what type of information is inside this envelope, or equivalently, what kind of service I'm trying to contact. And I could do this by specifying in words what's inside this envelope. Maybe it's something like HTTP, the prefix that you're familiar with from the web. Maybe it's an email. Maybe it's a chat message or the like. But if it is, in fact, something like HTTP, turns out the convention is not to use words, but to use numbers. And so, in fact, I need to put one other piece of information on this envelope, which is a so-called port number, a TCP port number, which is numerically printed after a colon on a virtual envelope like this. And in this case, I wrote 80 because 80 happens to be, by human convention, the number we humans agreed on some years ago identifies web services on servers. But this means that if the server I'm sending this to, 1.2.3.4, actually has other services on it, like a chat server and an email server and the like, this won't get confused with an email that I or someone else is sending to the server, or a chat message. The server will know upon receipt of this, oh, this is a request for a web page. Let me send this virtual envelope to the web server. But HTTP isn't the only such protocol. There are something called UDP, which is common in some circles as well. UDP works a little differently insofar as its feature is to not guarantee delivery. If some data gets lost, packets get dropped, so to speak, for whatever reasons, malfunction, technical difficulties, routers are overloaded, UDP says our protocol shall be not to retransmit that data. And that's a strange thing, because it sounds worse. And yet this protocol has been around for quite some time, still used, quite appropriate in some contexts. But what context would you actually want to just forge ahead, irrespective of getting complete information? Well, go-to here is something like video conferencing or audio conferencing or live TV on the internet, watching a game, like a football game, for instance. If you want to watch it in real time, you might prefer that the stream, the bits that are coming from the NFL or wherever to your computer, don't actually buffer, don't actually stall. You would rather miss a second so that at least you stay current in real time with that game. Or video conferencing, even more so. It's kind of annoying if you have a bad connection or some packets get dropped and you just have to wait and wait for the person's voice or image to be retransmitted. You'd rather just say, what did you say? Could you repeat yourself? Say again. You can just use human protocols to deal with that too. So sometimes you want live streaming applications for whatever purpose, and you want the data just to keep coming. As much of it as can make it through is great, but you don't necessarily want it to be resent. So data is going from one point to another, but how long does all this take? My God, this is kind of a long story just to get data there. Well, let's do an experiment. Let's go ahead and pull up a program that uses a different protocol altogether, ICMP, and there's other protocols still. This one's a little more technical, but it's wonderfully revealing in a few ways. I'm on my Mac here in a so-called terminal window, though you can pull up something similar on Windows and other operating systems as well. And what I'm going to do is literally trace the route between my laptop here and some foreign server, for instance, one on the west coast of the US, Berkeley's web server. So let me do that. Trace route, www.berkeley.edu, enter. And curiously, we start to see a whole bunch of lines of output, most of them numerical. And indeed, notice that each of these is an IP address. But what is it an IP address of? Well, we have like 18 of these between me and Berkeley, apparently. Turns out those represent routers between me and Berkeley, California. Each of them has an IP address, and each of them has a measurement of how long it took my data to get from my Mac to that router. It's highly variable. Notice it's kind of all over the place. In fact, this is just weird. This took like 3,000 milliseconds or 3 seconds. So I'm guessing that that router in row 8 was congested for some reason, some kind of network issue there temporarily, but then my data actually went through. And it's not cumulative. These are individual tests from my Mac to each of these routers iteratively, one at a time. And you can kind of get an aggregate sense of how long it takes, therefore, for data to get from the East Coast to the West Coast. If we look at some of the later numbers, they're kind of variable, but they seem to be around 75 milliseconds. So this is kind of extraordinary. If you want to fly from Boston, Massachusetts to like San Francisco, it's going to take you 5, 6, 7 hours. You want to send an email or send a packet, it's going to take you 75 milliseconds. Like, that's astonishing how quickly the data can transmit. Now notice this is not all that enlightening knowing these IP addresses, but eventually some of them have domain names. Just because the humans controlling those routers decided we are going to give these routers actual names, domain names, as opposed to just having IP addresses. And you can often, but not always, infer from the domain names where they are. So I'm going to guess that at least row 11 here, I don't know what xe7000.rtsw is, but LOSA.net, Los Angeles in California. I'm guessing my data kind of came into Southern California first, but then notice what happens next. A couple nameless servers, LAX. So maybe that's the airport. Indeed, routers for historical reasons tend to be named after nearby airport codes. I'm not sure what this next one is here, but I do recognize Oakland and UCB, UC Berkeley. So I'm guessing one of the next routers is actually in Oakland or near Oakland. And so that's a pretty long cable or interconnection essentially between LA and Berkeley. But the result ultimately is that my data makes its way to Berkeley, this time via this path. If I ran it again now or in a day or a week, the path might be a little different based on congestion and interconnectivity. But the data actually gets there. And cutely enough, it looks like Berkeley's web server is called CalWeb Farm, prod for production, ist.berkeley.edu. 75 milliseconds only. But what about this? What if we don't stop at the edge as we do at the edge of this continent, but keep going? What's going to happen? Well, let me try to trace the route to say www.cnn.co.jp, the domain name for what I presume is going to be the Japanese version of CNN's website in Japan. Here, too, we have a bunch of nameless servers just with IP addresses. Gets through them pretty quickly. We seem to have some lulls. Sometimes this program won't, sometimes the routers won't respond to these queries, so they remain essentially anonymous. But now this is quite interesting. Oh, my God. We went from routers 12, 13, 14, 15, taking about 63 milliseconds, give or take, to 193 milliseconds, which isn't a blip because it stays around that value, 180 milliseconds, 160 milliseconds, 177 milliseconds. That's a big jump of 100-some milliseconds just between routers 15 and 16. Why might that be? what could be between routers 15 and 16? Well, if you know your geography, it might very well be the Pacific Ocean. There's quite a bit of distance. There's quite a bit of cabling that actually connects the west coast of the country to Japan and other areas in Asia and beyond. And that's what's pretty amazing. Not only is there interconnectivity on the internet these days via cabling and via Wi-Fi signals and via satellite signals, via microwave signals and the like, you have so many different ways for data to be transmitted. And it's absolutely astonishing and exciting, dare say, just how interconnected the world now is. In fact, thanks to this animation online, let's take a look and appreciate just how extensive this network actually is. All right, so let's actually solve a problem now with this internet. Right? The internet, as you've probably heard, is filled with cats. And yet these cat images can be pretty big. And indeed, bigger still than images are things like video files from Netflix and the like. And so there's huge amounts of traffic transmitting over those kinds of interconnections. So how do we ensure, at least with high probability, that data can actually get through? How can we ensure that there's some form of fairness, if not net neutrality, so that my data can get just to its destination just as readily as your data can get there? Well, sometimes it's opportune to actually take big packets of information and chop them up. So indeed, what a computer will often do, thanks to TCP/IP, the combination of these protocols, is we'll take large files and large images in this case, tear them off into, say, roughly equal-sized parts, like this here, and then tear it down even further, perhaps, to get it into a smaller bite-sized piece, and then send not only one packet of information over the internet, but instead put one piece of information in this packet here, put one other piece of information in this packet here, whose addressing, both to and from, is identical, and then do the same thing for the two other pieces, so that ultimately we have 4 packets, each of which contains one portion, 1/4 in this case, of the resulting message, all of which are destined for the same destination. But the problem to be solved now is, what do you do with this information? If I have 4 seemingly identical envelopes, but inside of which are disparate pieces of information that somehow need to be reassembled, let's put on our proverbial engineering hats. How do you solve this problem? Is this sufficient information on the envelope so that if I send this out on the internet toward Berkeley or Stanford or Facebook or wherever, how does that recipient know what to do with it? Like, what would you, the human, do if you have not virtual but physical envelopes? Well, here too. And here's an opportunity really to bring to bear human intuition to a problem that seems fairly technical and well beyond one's own technical understanding. And yet, it really is just a technical manifestation of a real world problem. I need to keep these in order somehow. So you know what? I'm going to say something like 1 of 4 on the first one, like this. The next one, I'm going to say 2 of 4 on the next one, like this. And then I'm going to say 3 of 4. And then on the next one here, I'm going to put 4 of 4. And what's the takeaway now? Now, whoever is the recipient of these several envelopes as I send them out on the internet, and indeed, they don't have to follow the same path. One can go this way. One can be routed that way. Another can go to this router. Another can go to that router. Because they're all addressed, and because all of these routers are somehow interconnected, all 4 of those packets will hopefully get to their destination. But if they don't, the recipient can look at that additional detail I wrote on the envelope and see, ooh, I got part 1, I got part 2, I got part 3, but where is part 4 of 4? It didn't arrive because of congestion. Literally got dropped on the floor and not picked up. And so the computer, who's supposed to be receiving that data, thanks to TCP recall, can say, hey, please send me, again, packet 4 of 4. And so as technical as the internet might seem, it really, again, is just some fairly intuitive solutions to problems like this, albeit translated to more technical contexts, more technical protocols, and more technical languages. But let's look at some more user-facing protocols. The ones we've discussed thus far are fairly low level, if you will. And indeed, there's this whole internet hierarchy of protocols, layer on protocols, layer on protocols, so that what we humans really tend to care about, if we're not the engineers, but we're really the software developers and we're the users of applications, we care about application layer protocols that is right between the human and all of those lower level protocols. For instance, these, at least one of which has got to jump out at you, HTTP. Odds are you've seen this. Odds are you've typed this, though decreasingly you have to still type it because browsers will just add it for you. HTTP, the secure or encrypted version, HTTPS, IMAP for email, inbound, SMTP for email outbound, SFTP for secure file transfer, SSH for secure shell, an encrypted textual channel between two computers, and many more. But HTTP, let's focus on that one because that is Hypertext Transfer Protocol. Or HTTPS, the same, but the S stands for, not savings, secure. Secure. So it's actually encrypted in this case. So what does this actually mean? Well, at the end of the day, HTTP is a protocol that governs what kinds of messages go inside of those envelopes that I've been preparing for the internet. What kinds of messages go inside of those envelopes. And it turns out the simplest message that a computer sends through this whole internet ultimately, inside of that virtual envelope is quite often, thanks to HTTP, inside of this virtual envelope, if I'm trying to request a cat from the internet, might literally be a message like this. Get me, for instance, /cat.jpg for JPEG. And maybe some additional text after that, maybe some additional text below that. But at the end of the day, inside the virtual envelope, if I am on the internet and I'm going on Google Images and I want to find a picture of a cat, inside of my envelope, if I am a web browser, speaking HTTP, is going to literally be a textual message that says get/cat.jpg, if I know that's where the image is on some server. The response is going to be what was just inside of those 4 envelopes back from the server to me, chopped up maybe into multiple pieces, but in a way where I can then realize, oh, wait a minute, you sent me only 3 of 4. Please resend me the 4th one. So it works in both ways, whether it's me sending a cat to someone or receiving a cat from someone. This protocol, HTTP, governs how the messages are formatted and what language, so to speak, is spoken between web browser and server. So indeed, HTTP is entirely about having a web browser communicate with a server. And we can see this in action. I'm going to go ahead and pull up a so-called terminal window again, this textual command prompt on my computer, and I'm going to pretend to be a browser. So I'm not going to just trace the route between point A and point B. I'm actually going to request a web page as though I am Chrome or Edge or Firefox or Safari or whatever your favorite browser is. But of course, as before, all I know is that I want to visit my favorite website, facebook.com, for instance. But I don't know its IP address necessarily, so let's go through that step. How do I look up its IP address? Well, my Mac already has an IP address because of DHCP. I'm already powered up. I'm already connected to the Wi-Fi here on campus, and so I already have my own IP address. And I also have the IP address of a DNS server, so my Mac just knows that. But I can use that capability now to look up the name, the IP address for the name Facebook. And I'm going to do that as follows: NSLOOKUP for name server lookup. And I'm going to go ahead and type in www.facebook.com, enter. And interestingly, we get back this somewhat cryptic response, but let's make some sense of it. So it looks like the server that this response came back from is 10.0.0.2, which happens to be a private IP address here on campus that you might have in your own company or university or even home network. Then a non-authoritative answer is this: www.facebook.com, whose canonical name is, curiously, starmini.c10r.facebook.com. Well, it turns out that companies like Facebook absolutely have many, many, many different web servers. And they might not necessarily have just one IP address, but we might just be seeing one IP address depending on where I am in the world and depending on how Facebook has configured its infrastructure. The takeaway then is that apparently, so far as my Mac is concerned, www.facebook.com is an alias for, or a synonym for, this longer, less well-marketed domain name here. But what we really care about, if I'm about to pretend to be a browser, is this IP address. Facebook's IP address is apparently 31.13.65.36. And I can see this, in fact. Let me go into Google Chrome. or any browser for that matter, and go to http://31.13.65.36, enter, and voila, I made it to Facebook. Now, of course, no one in their right mind is going to advertise the IP address as 31.13.65.36. No one would remember that. We're not in the age of phone numbers on the side of billboards anymore. Now we have domain name system and DNS, which does this conversion for us. But now that I know that IP address, I can use this information and pretend to be a browser and not just see the response in Chrome as we just did, but I can see it in my textual window, so I can look inside the envelope. Indeed, this terminal window is going to let me pretend to send, well, actually send a message as though I'm a browser, pretending to be one, but it's going to let me see inside of the response that comes back. Here's what I'm going to do. I'm going to go ahead and type in curl-I, and I'm going to go ahead and type http:// and then that IP address. And I'm going to hit enter. And notice, uh-oh, Facebook has moved permanently. But this is a good thing. To where has Facebook moved? Well, apparently, we've gotten back a response via version 1.1 of via version 1.1 of HTTP that Facebook, per this status code, so to speak, has moved permanently. Has moved permanently, which sounds scary, but where has it moved to? Oh, they don't want people visiting their IP address, even though it works. They want to redirect people, so to speak, to their domain name. So we seem to be kind of in a cyclical situation here where, wait a minute, I thought I had to convert my domain name to an IP address, and indeed I do, but it turns out curl is pretending to be a text-based browser here effectively, and it is already going to do this DNS lookup for me, so this is OK. I'm going to go ahead now and do curl-I http://www.facebook.com, enter. Oh my God, Facebook moved again. But where did they move this time? Well, it seems that Facebook would prefer that we visit https://www.facebook.com, which is the secure, the encrypted version. OK, I can oblige. Let's go ahead and do that. Curl-I of the HTTPS version, which I've just pasted in, enter. And voila. Now, this looks overwhelming. But what's really important is this message here. It turns out everything is OK. And indeed, what's come back from the server is a virtual envelope, inside of which is this message here saying, hey, no big deal, everything is OK. And you never see this number when you visit web pages, unless you're a software developer and you know what tools to use. Instead, some of us out there, some of us normal humans, occasionally see a different number. It's maybe the one number you associate with the web. Let me simulate it as follows. Let me go ahead and request this completely bogus page. Hopefully, that's not actually someone's username. And hit enter, scroll back up a bit. What do you notice this time? If you've ever wondered what 404 means, it is the numeric code inside of a virtual envelope coming back from a server when you have requested some nonsensical URL because of a typographical error or just nonsense that I typed that's now having the server tell you, not found. 404. So this is just a special numeric code. And this is common in programming to have numbers correspond to different types of things that can go wrong, or better yet, that can go well, as in the case of 200 OK. Now, all of this stuff is called HTTP headers. So I was oversimplifying earlier when I said HTTP is just this handshake of sorts between servers where you say, get me a cat picture, and then you get back the response as per those 4 envelopes. There's more headers. There's more key value pairs, words with colons, words with colons, words with colons, and then values to the right of those. And that is just additional metadata, more information from the server that tells you a little something about it. But if I instead run that same command one final time, this time doing curl, and then specifying not -I, but just the URL itself, and hit enter, this craziness comes back. And this looks like a whole lot of programming language in something called JavaScript, or big JSON object. And my God, look how much data came back from the server. But notice I'm starting to see some structure. Open bracket div, and the word label here. And if I go up here, input here. And indeed, what you are seeing is a language called HTML. Inside of the virtual envelope, if you're requesting not a cat image, but a web page that has your news feed or your inbox from Gmail or your search results from Google, is a language called HTML. And HTML is not a programming language. And indeed, it's not as cryptic looking as this. Google is being or Facebook is being very efficient when it comes to showing me this information and just getting rid of as much formatting as they can to save space, to save on internet bandwidth, the transmission thereof. But it's a language that comes back in this virtual envelope that a browser knows how to display. It's a markup language in the sense that it's going to tell the browser what to show on the screen, where to show the cat, where to put words, whether to make those words big or bold or italics or centered or any number of other things. And indeed, what you are seeing is this. This is www.facebook.com graphically as we see it in the browser. Underneath the hood is that black and white, seemingly nonsensical Greek, if you will, that at first glance, there's no way most of us would understand it. But that's because we're looking at it here. We need to dive in a little deeper, take a look at what HTML is, how it's actually structured, make the simplest of web pages, a hello world of web pages, if you will. And then can we realize and build back up to this point exactly what composes pages like Facebook and Gmail and Google and Bing and others. Because at that point, we'll have understood not only how the internet works, but how you can use it as a delivery vehicle for your ideas, for your programs, for your products, for your companies and more, and actually deliver information and deliver cats and much more to your users on this internet.